Hi. Very good afternoon to everyone watching this discussion, and thank you for joining us on our panel where we interview experts in fields such as digital manufacturing and security. My name is Dr. Susheem Kanwar, and I'm a postdoctoral researcher at the NYU Tandon School of Engineering. Before we begin, first let me thank the sponsors, specifically the National Science Foundation, without whom events like these wouldn't be possible. This webinar is going to be recorded and posted onto both our YouTube as well as our website. We are joined here today by Professor Rong Yang from Cornell University. Thank you for joining us today, Professor, and thank you for taking time out of your busy schedule for us.
Thank you, Susheem. I really appreciate this opportunity to talk about our project.
Of course. So before we begin, could you please give a brief introduction about yourself, if you don't mind?
Of course, yeah. I am Rong Yang. I'm an assistant professor in chemical and biomolecular engineering at Cornell University. And my group is the Laboratory for Biointerface Engineering. So we are very interested at the biointerface where synthetic materials meet and interact with living organisms, tissue, and sometimes living animals. And we're driven by a whole range of practical problems from biofouling to drug delivery to infectious disease, and very happy to be here today.
Thank you so much for that introduction, Professor. Your group is currently working on an NSF project which deals with scalable precision manufacturing of polymers guided via artificial intelligence. So could you please explain more about that project, as well as how did you become interested in a project that is at the intersection of artificial intelligence and manufacturing?
Absolutely. So it is a collaborative project among my group and the groups of Professor Nicholas Abbott, who is also in the Smith School of Chemical and Biomolecular Engineering at Cornell, and the group of Professor Fengqi You. So he is an expert on AI and machine learning, and also the group of Professor Yang Ganser at North Carolina State University. He's also a chemical engineer, and his group specializes in interfacial surface functionalization, and he has this very cool technology on creating gradient surfaces, which we're using to combine with the expertise from the Abbott group in liquid crystal to generate the optical output that will be read by AI. And one of our group members is also, team members, I should say, is also Professor Alison Godwin, and she's an education research expert. So she helps us develop that whole program on workforce development and training to bridge the gap between manufacturing, polymer science, and AI, which is what we believe to be the future workforce, the need of the future workforce that could help carry on the research discoveries into the real world. And the overall premise of the project is that we're going to use AI, and especially the image recognition capability of AI, to read the optical output that is generated during polymer synthesis, and to guide the condition selection on the fly. So if you're shooting for a particular set of material properties, say in our case, it's the polymer nano or microparticles used in drug delivery, and we want a very specific size and shape of this polymer particle so that you can predict the things like the pharmacokinetics of these particles once you ingest it or inject it. And what are the conditions, synthesis conditions that you can use to hit that target? So this capability does not exist right now, and we think that's where AI could make a big impact. And to generate these optical outputs that can be read by AI, we're leveraging liquid crystal. And you may have heard of liquid crystal as a material for display, computer display. I think back in the days, it's made of liquid crystal. And to tie the optical output then to polymerization, we're using MyLab's technique. So we specialize in this technology called initiated chemical vapor deposition, or ICVD is how we usually refer to it. It's a technology that is similar to what's used in the semiconductor manufacturing for CVD of computer chips, but we use a much lower temperature version of it so that it's compatible with polymer, which is plastics and rubber, you know, these low materials that have a rich collection of functionality, but perhaps not as thermally resistant as metal semiconductors. And the reason we need ICVD in this scenario is because we get to deliver the reactants in polymerization. These would be things like monomer initiator, small molecule feed in the vapor phase. And these vapor phase molecule would then partition into the liquid crystal display continuously to drive that continuous synthesis, continuous manufacturing of polymer, and while generating this rich optical output that is indicative of the polymer particle size, shape, and surface chemistry. This output would be too complex to read with our naked eye, but with the help of AI, we are building that closed feedback loop that the AI image recognition will tell us what we're synthesizing in that moment, even on the nanoscale, and then help us pick the right synthesis conditions to hit the target set of properties. And a really important role played by the Genzer group at NC State is that they create interfaces that guides the organization of the liquid crystal. So in this case, liquid crystal serves as both an optical output provider and also a template for polymerization. So we have some knobs over the liquid crystal structure through the interfacial engineering techniques. And Professor Godwin, our education research expert, is in every step along the way, talking with our students. We're kind of treating this whole group of trainees, graduate students, postdocs, and PIs as a living laboratory, if you will. We are the subject of study for Professor Godwin, and she, I think, is being very productive, and she put in a few conference papers already about her discoveries, how interdisciplinary, for example, interdisciplinary research can help shape the identity of the trainees and how then that identity-based motivation for doing research or continue to pursue your thesis plugs into the professional growth, and academic growth of the participating students. So it's a very integrated group from different disciplines.
Oh, thank you for such an excellent overview of your project, Professor. I really appreciate it, as do our viewers. What would you say your project is at in terms of like the stage of completion? And when it comes to dealing with the data you've generated for the AI models, for example, how would you say that's coming along, or at what challenges have you faced in generating that data?
So the question is how far along we are in the grant and in how, what are some challenges and lessons we learned while generating the data for the AI model.
Right, that's correct.
So right now we are 2 years in. So the grant started in 2023 and January 1st, 2023. So we're about a little over the halfway mark. And it was a surprise to me, I guess, because of my inexperience, that it takes some time for everybody to get on the same page and speak the language. I would say for the team members, for I to learn liquid crystal, how they interact, the type of molecular interactions that is in there, and the AI language, right? I don't think I have fully mastered it. It takes quite some time. So I would say that is a challenge that we encountered, but I think after 2 years, the team is working really, really well together. So we're right now just hitting that period where the team is very productive and we're starting to put papers together and from different groups and all working together. And the data generation, it does take a lot of time. And I'm lucky to have excellent collaborators and team members on this project. So the optical signature that I talked about that is so critical for the to connect, to close the feedback loop on the AI front, that actually is done on two fronts to expedite that data collection. One is the in situ imaging with ICVD. So we purchased this new equipment where we can observe and capture the real-time video while we're operating the ICVD machine. So that's one piece where we generate a lot of in situ video. But with that in situ microscope, because of the need, sometimes there's conflicting needs of doing reaction, doing polymerization while doing the imaging. We don't get the highest quality of videos. And then there's a parallel track where in the Nick Abbott's group, we have a dedicated students playing with the liquid crystals and using the model polymer particles. So these are, for example, particles that present the set of targets that we're interested in to disperse them in the liquid crystal and then capture a large collection of images for the target properties that can feed into the AI training model. And a third prompt for in our data generation process is by data generated by AI, right? Especially in this day and age with that initial seed collection of images. Professor Feng Qiyou's lab is actually taking those initial libraries, could be hundreds of images, and then plug them into the most advanced AI model that is pioneered by his group to generate a much larger library. And we're validating those AI generated images and see if that is a valid approach for us to train an AI model. So we're taking all these different angles to help expedite it. But it's definitely, that's a very time consuming task.
Yeah. Well, I find that quite fascinating how you've been able to use your expertise in, let's say, biomolecular and chemical engineering and collaborate with people who do artificial intelligence. That's pretty fascinating. And how would you describe, I mean, especially in these kinds of projects which span over the course of like multiple years, how would you describe a typical day in your line of work? And what is it you enjoy most about what you do?
So what I enjoy the most about what I do is actually just listening to all the different updates in different areas of the project and learning the different aspects. That has just been really fascinating to me. And a typical day, for example, today we had our team meeting with the big team, all 5 PIs and all the trainees and postdocs. We meet on Zoom since we're from a couple of different institutes. And we have roundtable discussion to start off the meeting, and then we will really drill deep into one of the areas, one of the aspects. Today was an update on the liquid crystal front, but the student working on it actually had to learn a lot about polymer synthesis using CVD and AI imaging. So it was quite involving. It's kind of all hands on deck. It's really enjoyable to me to kind of interact with this broad cross section of students and researchers. And I also spent a lot of time meeting with different students and different groups from different groups. A lot of discussion, especially when at this point of the project, when we're ready to put together manuscripts, it takes a lot of time to iterate on the figures and the drafts. And teaching is also a big component because workforce development is an essential piece of this grant, right? So I have incorporated polymer manufacturing into the class that I'm teaching this semester, actually. So in the spring, I teach polymeric materials, and we're doing a theme on sustainable polymers because polymer has a bad reputation in the days in public media. You hear about these like forever chemicals, PFAS, that can come off of polymers. So a new ingredient that I'm introducing into my class is to discuss polymer manufacturing extensively and then help students think through what are the improvements that they can do to the polymer manufacturing processes to make it more compatible with the long-term well-being of humanity, I guess.
Wow.
Yeah.
So something that is really the need of the hour, given the focus on sustainability these days.
Yeah.
And what would you say are some of your important contributions in this area, or things that you consider you've contributed in this area?
So in terms of polymer synthesis and manufacturing, I have a lot of faith in our technology, ICVD. I think it's highly scalable because of all the similarities between the CVD technology used in semiconductor industry and what we are using right now. So I think it has a lot of promise of making a big impact in the precision synthesis, especially of polymers. And CVD traditionally is viewed as a thin film synthesis technology. So what I'm really excited about what we're doing right now is that we're introducing that additional dimensions into this thing, kind of bring it from a 2D plane to a 3D space. And that's what we're doing with this liquid crystal templated polymerization. We can, for example, leveraging the elastic energy to constrain the polymer growth, or we could use mechanisms like de-wetting, phase separation to create polymer particles with this scalable and precise technology. So I think it has a lot of potential, especially in the manufacturing space.
Okay, that's wonderful. And how would you describe, or in your opinion, what would you say has been the biggest learning curve in this field of AI-guided scalable precision manufacturing? And how do you see this field shaping up in the next 5 to 10 years, let's say?
That's a really good question. I would say the biggest learning curve for me is that gap, because I am trained as someone who does polymer synthesis a lot, right? I know my language around polymerization, but AI is definitely something that I have to learn
Yeah.
for this project. So that is also the bridge we're trying to build, I guess, with our workforce development plans. And in the next 5 to 10 years, what do I see as the biggest the future direction, is that right, for
Yeah.
the field of precision polymer manufacturing and polymer particle synthesis? I would say I would really hope that with the scalability of this technology, which I just talked about, and with that continuous feedback loop that is accelerated by AI, we're hoping to bring this platform into the real manufacturing practice more quickly, because usually it takes, decades for an experienced practitioner to accumulate the knowledge to say, okay, you need to design the manufacturing process in this particular way. Here is a set of parameters you want to use, right? But now with the AI, can read the material properties, if you will, in real time, and it can help you guide the selection in an automatic way. I think that learning experience, that know-how, accumulation of know-how will be greatly accelerated. And I think that will happen in the next 5 to 10 years. And that
Wow.
will really revolutionize the manufacturing landscape.
Definitely would be looking forward to it. And finally, what's one piece of advice you would love to give to young professionals entering this field?
One piece of advice I would love to give is also something I learned from working on this project, which is to not be afraid of marching into a new area, right? Especially in this day and age. You may be more comfortable if you're like me with chemistry, but you will just have to pick up all the AI language along the way, and vice versa. Maybe
Yeah.
you're more well-versed in programming, but chemistry, just another language that you can pick up.
Wow, that's a very interesting perspective and way to look at things. Thank you, Professor, for your time.
Yeah, of course. This is really fun. And thank you so much for spending the time.
Thank you.